Hey everybody, by the end of this video, you should be able to describe the electron cloud model of an atom, what a shell, subshell, orbital, and spin of an electron is, and this will introduce you to the idea of electron configuration. So, up until now, we've been talking about atoms in general, but I think it's very important for us to understand that the electrons are probably the single most important thing in an atom because they are responsible, for the most part, for most of the chemistry that is happening around us. Okay, so finding out where electrons are is important. And so we go from here talking about where electrons are, and then eventually we're going to start drawing pictures of atoms or of molecules so we can figure out where the electrons are. And so it's just this idea of tracking electrons just to figure out where they are. Okay, and so we have to get some terminology down in order to do this. And so we have to realize that electrons exist in shells, or what you'll hear me describe as energy levels. Okay, now back in the day, you guys used to draw electrons like that, or atoms like this. Okay, this was what we call the Bohr model. This is not the correct model, but this helps us to kind of visualize what's going on here. And so here would be the nucleus, and then you'd have an electron zipping around. Okay, sometimes they would call this the planetary model because electrons go around in circles like this. Okay, but the problem with that is that an electron doesn't move in one or in two dimensions. An electron moves in three dimensions. So you go and you talk instead of about orbits or about these things here, we call them shells because it's a three-dimensional thing, kind of creating a shell around the nucleus, or if it's in this second energy level here, it's creating a shell around whatever's underneath it. And so you have these shells. And then, of course, to make things overly complicated, not really overly complicated, I just say that, but okay, but just to keep things as organized as possible, the shells are then divided into subshells. And then each subshell is divided into orbitals, and then within the orbitals, electrons have a spin, okay? And so this allows us to identify values to each and every electron that is within an atom. Now, the point here is that electrons, if we have the nucleus, and I'll do my electrons in red, the electron is moving all over the place. Back. So the electrons are moving all over the place, around and around and around and around. And so what we know from doing the math is the electron is 95% probable to be found in a place that's defined by the shell, subshell. It's not absolute that it's going to be found here. Could it be found out here 5% of the time? Sure. Okay, but as the electron is moving around and around and around and around and going, around here, it could zip out here. It could zip out here. It could zip out here. Okay, there's all sorts of things that can happen, but 95% of the time, it's defined by the shape that it is of the shell, subshell, orbital, and the spin. Okay, and so that's what this model shows. It shows that the electron is always moving. It's showing how it's moving, and it's giving us the idea that an electron can move anywhere, but is likely to kind of have a certain path within the electron or within the atom. Okay, and so let's talk about shells. Okay, the outermost thing. Okay, the biggest thing is These are the outermost shells, and they can be labeled anywhere from 1 to infinity, but usually it's up to 7. Okay, so if we think about kind of the classic model, because the Bohr model helps us when we do this. If we think about the Bohr model or the planetary model, where we have these things, okay, so the idea is that each one of these things is a shell. Well, typically we usually only go up to 7. We only have 7 of these things in an atom. Electrons can move, like I just said, so the electrons they could go out to 8, 9, or 10 or whatever. But typically we only go up to 7. And you'll see me say N equals 7 because the symbol for energy level or shell is N. Okay? And so so that's kind of the standard distance. So let me make sure that I got that right. 1, 2, 3, 4, 5, 6, 7. Okay. And so using the periodic table, you can determine what energy level it is, what energy level the electrons are in, by looking at the row of the periodic table. Now, there's going to be more on this later because all of this is building into the really neat thing about electron configuration. Okay, but and each shell has a limit to how many subshells it can have. Excuse me, I'm getting over being sick a little bit. And it's actually really easy to determine how many subshells. When you have the first energy level or the first shell, that can have 1 subshell. The second energy level can have 2 subshells. The third energy level, you guessed it, can have 3 subshells. The fourth energy level can have 4 subshells. On down the line. Oh man, I am so sorry. Okay. And so what is a subshell? Well, a subshell defines the shape where the electron moves around. And so kind of the easiest shape is if we have the nucleus in the middle, and again, just because I want to do this, the easiest kind of shape, which is one of them, is a sphere. It's not a circle, it's a sphere because it's 3-dimensional. Okay? And so a subshell is really a shape. And then we denote, or we identify each of these shapes by a letter. And so the 4 that we have shapes are S, P, D, F in that order. Okay, I know you would think that it's an alphabetical order, but but it's not. And so an S is one shape, a P is a different shape, a D is a third shape, and an F is a fourth shape. Okay. Each subshell, there's a limit to the number of orbitals that are in each subshell. So an S, there's actually just one of these S's, okay? And then there's 3 P's and 5 D's and 7 F's. And isn't that odd? Get it? 1, 2, 1, 3, 5, 7. Okay, anyways. And so we can determine what subshell it is by where the element is located on the periodic table. We can determine which subshell the electron is in based on where the element is on the periodic table. Okay, and again, this is going to go into electron configuration. So that's subshells, and then within each subshell, there's something called an orbital, and that's the individual shape. That's the individual space. And so the S's, just to give you an idea, are spheres. And so a sphere can really only be oriented in one direction in space. Okay, the P's, these guys are what we call dumbbell shaped, and there's more on these specifically a little bit later. And then the D's are these clovers for the most part, and the F's are kind of double clovers, so they go this way, and then there's clover going around the outside here. There's better pictures coming up, and so this is kind of where I describe them, SPDF, okay? Dumbbell, we call them dumbbell, but it's not really like a dumbbell like this, okay? It's not like that. It's more like a double teardrop like that, okay? That's not really a dumbbell, but that's just the way it works, okay? And so here's an s orbital, and these are the most studied of the orbitals, and so I could find a lot of pictures about what's going on, okay? And so here in the green, you can see that it's showing one electron moving all around so that it looks like a cloud. And it's not a cloud, it's just the way that one electron, it's like taking a picture 1,000,000 times and putting each of those pictures over that. Notice that most of the electron cloud is here, but if you look really carefully, there's an electron that sometimes it falls out here, sometimes it falls out here, sometimes it falls out here. Okay? And that's the idea of the probability. Now, one of the questions you may ask is, what happens, so you have an s orbital, but what happens when you get into the second energy level? The second energy level has s's and p orbitals, okay? But there's a 1s, there's an s orbital in the first energy level and an s orbital in the second energy level. So look at what happens here. I'll make it in black so it's a little easier to read. Here is your 1s orbital, and then there's kind of this empty spot in here. And of course, remember, it's just a probability. So this is a little emptier. And now here's your 2s. So you have a sphere within a sphere. It'd be like a golf ball inside a tennis ball. Okay, or those Russian nesting dolls, that's kind of they're called marushkas. That's kind of what's happening here. And so you have a 1s, the first energy level, with its electrons moving around, creating this thing, and then kind of a little gap here, and then the second energy level with its s orbital kind of surrounding the first. And so that's the way an s orbital looks like. Okay, now these p orbitals are dumbbell shaped, but there's 3 of them. Here we go. We got 1, 2, 3. Okay, now the p orbitals, they are just oriented they're pointing in different directions. We would say, to make it really complex, they're oriented differently, but the idea here is here's one along the x-axis, here's one along the y-axis, and here's one coming out of the computer screen in the p or in the z-axis. And so we have 3 different orientations of the same shape. If we go back, a sphere can really only have one shape. You can't move it in any way to make it look different. But here, it happens that there are 3 different shapes within the p's. So the s's, there's 1. The p's, there's 3. And then the d's, there's 5. Okay, and this is what I mean, that they're mainly all clover leaves. Okay, there is this one that's like a donut. Okay, and it's got the donut ringing around it. Okay, and I don't care what these are. Just know that the D's are clover leaves. Okay, and then the F's. Here we go. The F's are really crazy. There's these double donuts here, but most of them are these like double clover leaves. They look like 8 balloons kind of all attached in the middle, and they all kind of take different orientations. Again, the 2 that I'm most concerned with, that the shapes of, are the S's and the P's. The D's and the F's, it's just good to kind of have a frame of reference for it in the back of your head. Okay, and so each orbital, okay, let me go back here. Each orbital can hold 2 electrons, and it's not because of its shape, it's just because of its space. So this s orbital, how many s orbitals are there? There's 1 in each energy level, so there can be 2 electrons in this s orbital. In the p orbitals, how many p orbitals are there? 1, 2, 3. Each one, there can be 2 electrons in this one, 2 electrons in this one, and 2 electrons in this one. So the p's can hold 6 orbitals, or 6 electrons. And there's 5 of these. Each one of these can hold 2. Don't get confused by the number of little balloons that are attached here. It's still only holding 2 electrons. The electrons just happen to move in this kind of funny shape all around. Okay, so there's 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons. So this can hold 10 electrons. And then the F, there's a 7th F orbital here that's another double clover that's flying over here. But regardless, this can hold 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons, and then the 7th one can hold 2 electrons for a total of 14 electrons. Okay, and so let me just really quickly do something what I think is super awesome here. Okay, let's go to the periodic table. The s orbital, how many s orbitals are there? There's 1. And how many electrons can they hold? They can hold 2. Is there a coincidence that this side of the periodic table is 2 atoms wide? What about this side of the periodic table? How many elements wide is it? Let's see, 1, 2, 3, 4, 5, 6. The p's can hold how many electrons? Oh, 6, because there's 3 orbitals within the p subshell. 3 orbitals, 3 times 2 can 6. There's definitely a pattern shaken out here. How many here? This, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, 10. Okay, well, 10 electrons. That's the d orbitals, right? Because the d orbitals have, there's 5 of them, and each of those orbitals can hold 2, so 2 times 5 is 10. Oh, this is crazy. And now, well, maybe we don't have to even worry about this, but let's see. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14. All of these guys down here, there's 14 electrons down here for the lanthanides and the actinides, and that's because they're f orbitals. So there's a pattern to the periodic table above and beyond just kind of the pattern that you have learned previous to this. And the pattern is fascinating. It has everything to do with how the electrons are arranged. Okay, but I'm not going to get into all of that in this video because there's just too much. Okay, so let's just quickly make sure that we know why we're doing this. So what? Okay, we are doing this so that we can locate every atom, because the primary reason that chemistry happens is because electrons are moving around and doing stuff. Okay, and we need to find out that every electron is different. Okay, we need to identify all the electrons, and then we realize that when we do this, every electron is different. Okay, every electron is different, and then we can say that, well, the primary reason why chemistry happens is because the electrons are doing things. Okay, I would say that 99% of the chemistry that is actually done, like real chemistry that's actually done, we're not talking about like rolling marbles and dropping marbles and, you know, painting a board or anything that we've done up to, you know, like fictitious things. Like when we go and blow things up in the lab, it's all because of the electrons. 99% of the chemistry that's done is because electrons are moving around. Okay, and so stay tuned. We'll get to the second, more exciting video next.